Hello and welcome to another video. In this video, we are going to be exploring limits. We are going to be talking about what a limit is, and we are going to be looking at some specific examples of the kinds of manipulations that we can do to the different functions in order to compute the limit of a function. And so without further ado, let's get into it. First of all, what is a limit? A limit is a way of looking at where a function is heading without actually analyzing where the function is. And I know that this might sound a little strange, but let's just draw a quick diagram here on the right-hand side. And here we have a function. And let's just pick a random point on this function. And we want to think, okay, here we have a value of x that is equal to a, so the equivalent y value, let's call it f of a. And we want to ask, where is this function heading? As x approaches a, what is happening to the function? And so visually, we can just follow the function, right? And we are going to see that it's approaching this point, f of a. And so we are going to be looking at what the function is doing, at where the function is heading, right? But we are not going to be focusing specifically on that point. We are not just going to get here and be like, oh yeah, it's at that point, it's at f of a. We are going to go through it and we're going to say, oh, it looks like it's approaching f of a. That's the direction in which it is going. Okay, and that is exactly what we are going to do, except that we are not just going to be doing this visually, we are going to be doing it algebraically. But before we do that, there's a couple of definitions and notations that we have to establish. So f of a denotes where the function is at x is equal to a. So f of a is the value of the function when x is equal to a. And then the limit, the notation for limit, is as follows. The limit as x approaches a, and so we write limit on the top, and then as a subscript almost, we write x arrow a to indicate that x is approaching the value of a of f of x. So this denotes where the function is heading as x approaches a. And we read it as the limit as x approaches a of f of x. Or alternatively, we read it as the limit of f of x as x approaches a. Okay? And so visually, like I just showed you, if we have the graph, we can find the limit of a function quite easily. Of course, some functions might be a little trickier than others, especially if they are not continuous functions. And that is a topic for another video. But algebraically, this is a little trickier. And there's a couple of rules or a couple of steps that we need to remember. Okay, so when we are working with limits, the first thing that we want to do is to try and sub in the condition for x. Okay, so if we can sub in the condition for x, then we should do that. If we can let x be equal to a, and that works out, then that is the value of our limit. However, if we cannot sub the condition in due to math rules, for example, if it's going to result in division by 0, or if it's going to result in a negative number under the square root, then we need to manipulate the function so that it looks different. And we then try to substitute once we manipulate the function. Some examples of manipulations include factoring, finding a common denominator between two expressions, two fractions, and rationalizing. And this is why we have a video on the rationalization of expressions so that we are more easily able to then use this skill now when dealing with limits, and I will link that video to our description below. So let's take a look at a couple of examples here. The first one, we have the limit as x approaches 3 of x cubed. Okay, so let's try the first step, just directly plugging in x is equal to 3. And so we are going to get right here, so we have the limit of x is equal, of x approaches 3, of x cubed. And so now here, let's just sub in x is equal to 3 into the expression. So we are going to have 3 cubed, which is going to be equal to 27. And so here we do not have any hiccups, right? We have a number, 27. We're not dividing by 0. We don't have any negative numbers under square roots or anything funny like that. And so this is the value of our limit. The limit as x approaches 3 of x cubed is equal to 27. And again, this makes sense because the cubic function is a continuous function, okay? And so for the most part with continuous functions, we are just going to be able to directly plug in the values of limits without having to manipulate them too much. Let's take a look at another example. Slightly more complex. Now we have the limit as x approaches 2 of x minus 2 over x squared minus 4. And so what happens here if we let x be equal to 2? Well, we are going to have 2 minus 2 over 2 squared minus 4, which is going to be equal to 0 over 4 minus 4, which is equal to 0 over 0. And we cannot divide by 0, right? So this is definitely not the right approach. And so what are some of the manipulations that we have talked about? We have talked about factoring. We have talked about finding a common denominator, and we talked about rationalizing. Rationalizing here doesn't make sense because we don't have any radicals to begin with. Finding a common denominator also does not make sense because we have only one fraction, right? There's no other fraction to find a common denominator to. And so we are left with factoring. And if we actually take a closer look at the expression that we have here, we notice that the denominator is in fact a difference of squares, right? And so that tells us that it is indeed factorable. And so let's do it. Let's start by rewriting the expression as given. So the limit as x approaches 2 of x minus 2 over x squared minus 4. And now we can factor it. As a difference of squares, we are just going to take a negative term and a positive term. So that's going to give us x minus 2 times x plus 2. And now we might notice that we can cancel out the numerator with one of the terms in the denominator. And this is going to give us the limit as x approaches 2 of 1 over x plus 2. And now we should be able to directly plug in the condition for x, which is just 2. And so that's going to give us 1 over 2 plus 2, which is equal to 1 over 4. And here again, that is the right answer. We're not dividing by 0. We do not have any negatives under a square root. That is just the value. So after we have manipulated the expression, we are able to directly plug in the condition for x to find the limit. And so right here in this case, the limit as x approaches 2 of x minus 2 over x squared minus 4 is equal to 1 over 4. Now let's take a look at another example. This time around, we have the limit as x approaches 0 of 1 over 1 plus x minus 1 over x. And so this is what we call a complex fraction. And again, we might first want to try and plug in x is equal to 0 just to see if it works. Of course, we can almost immediately see that's not going to work because it's going to have us divide by 0. But nonetheless, let us do it just so that we actually see it. We are going to have 1 over 1 plus 0 minus 1 over 0. And here, of course, we are dividing by 0, which is a big no-no. And so now here we have to think about how we can manipulate the expression so that we can get rid of this x here in the denominator, right? And so instead of just focusing on this x, we kind of want to look at the numerator, right? And here we see that we have a fraction minus a whole number, and we might want to try finding a common denominator between the two terms, okay? So let's give that a try. Again, rewriting the expression first. So 0, 1 over 1 plus x minus 1 all over x. And now we want to find the common denominator. And what we might observe here is that 1 is the same as having 1 over 1, right? And finding the common denominator is going to require us to multiply both the numerator and the denominator by the denominator of the first expression, which is 1 plus x. And so let's do that. Here we are going to have the limit as x approaches 0 of 1 over 1 plus x minus 1 plus x over 1 plus x all over x. And this is going to be equal to the limit as x approaches 0 of 1 minus 1 plus x. And here note that we do have to put that second term in brackets because that negative sign affects the entire numerator. It's not going to affect just that 1, but it's also going to affect the x, right? And then this is going to go all over the same denominator, which is 1 plus x now. And then that whole expression is going to be over x. So now simplifying here a little bit, this is going to be equal to the limit as x approaches 0 of 1 minus 1 minus x, right? So here the 1's are going to cancel out, and that negative sign is still going to affect the x. And so I'm going to have negative x over 1 plus x all over x. And so now I want to undo this complex expression, right? And so here I'm going to rewrite the denominator as x over 1. And why is this? Because if we recall, having technically a complex fraction is a division of two fractions, right? Is a fraction divided by another fraction. And when I have a fraction divided by another fraction, what I can do is that, so here I'll even rewrite it as such. Having a over b over c over d is the same as having a over b divided by c over d, which I compute by actually keeping the first fraction, and then the division becomes a multiplication, and then I flip the second fraction, right? So this is what is known as keep, switch, flip. And that's exactly what we are going to do here with the expression that we have. So we are going to keep the fraction in the numerator, which is going to be negative x over 1 plus x. We turn the division into multiplication, and then we flip the fraction in the denominator. And here we can see that we are able to cancel out those x's, and that is going to leave us with the limit as x approaches 0 of negative 1 over 1 plus x. And now we can try again to plug in x is equal to 0 into the expression, which is going to result in -1 over 1 plus 0, which is equal to -1 over 1, or just simply -1. And so we can see that we have manipulated the expression successfully to find the limit as x approaches 0 of 1 over 1 plus x minus 1 all over x. And that limit is equal to -1. Right? So again, a different algebraic manipulation here. And then we have one more that we haven't discussed yet, and that is rationalization. And so let's think that we have an expression such as this one, the limit as x approaches 0 of 16 minus x minus 4 all over x. And again, here we might try to directly plug in x is equal to 0. But if we do that, then we are going to end up dividing by 0, right? We are going to have the square root of 16, which is just 4, minus 4 over 0. And again, it's not even worth it for us to simplify it further, because immediately we see that we are dividing by 0. But if we do, we are going to get 0 over 0, which again, we do not want. That doesn't tell us anything. And so we're going to have to manipulate this expression, and as soon as we see radicals, we should be thinking rationalization, okay? And so here we go. Let's rationalize this numerator. So we have the limit, always starting by rewriting the expression given. We have the limit as x approaches 0 of 16 minus x under the square root minus 4 all over x. And so again, remember that in order to rationalize an expression, we want to use the conjugate, right? And so the conjugate in this case of the numerator is going to be the square root of 16 minus x plus 4. And so we're going to both multiply and divide by this amount, because again, this is the same as multiplying by 1, right? I am not altering the initial expression in any way, shape, or form, because I'm basically just multiplying by 1. And so here we go. Using distributive property, right? We are going to have the square root of 16 minus x minus 4 times the square root of 16 minus x plus 4 in the numerator all over x times the square root of 16 minus x plus 4 in the denominator. And as I was saying, we are going to need to use the distributive property in order to expand and simplify this expression in both the numerator and in the denominator, right? And so here we are going to start with that 16 minus x under the square root, which we are going to multiply with the 16 minus x in the second term. So the square root of 16 minus x times the square root of 16 minus x, this is simply going to be equal to 16 minus x, right? So again, writing the limit as x goes to 0, because we're not actually evaluating the limit yet, so we gotta include that notation still. So the limit of 16 minus x, and now here we are going to multiply 16 minus x by 4. So this is going to be equal to plus 4 times the square root of 16 minus x. And now we go with the second term. Now negative 4 times 16 minus x. So that's going to be negative 4 times the square root of 16 minus x And finally, we are going to be multiplying -4 and +4, which is going to give us -16. And this, of course, all over x times the square root of 16 minus x plus 4. All right, and so now let's simplify this numerator here. We can cancel out the +16 with the -16. And of course, we can also cancel out the +4 root 16 minus x with the -4 root of 16 minus x. And this is going to leave us with a negative x in the numerator. And we haven't really touched the denominator, so we're going to have x times the square root of 16 minus x plus 4. Just going to fix the brackets there in the previous one. There we go. Now the bracket is in the correct spot because that x is multiplying both the square root of 16 minus x and that 4. All right, and so now we can see that we can cancel out the x in the numerator and the denominator, which is going to give us the limit as x approaches 0 of -1 over the square root of 16 minus x plus 4. And so now I should be able to just let x be equal to 0, right, without any issues. So let's give that a try. We are going to have -1 over 16 minus 0, all under that square root, plus 4. And this is going to give us -1 over the square root of 16 minus 0 is equal to the square root of 16, which is equal to 4. So here, 4 plus 4 is going to be equal to 8. And so we are going to have -1 over 8 as the limit to this expression here. Okay, and so the limit as x approaches 0 of the square root of 16 minus x minus 4 all over x is equal to -1 over 8. And this concludes the different examples of manipulations that we can make to a function in order to compute the limit. Okay, so the 3 types of manipulations, again, just to recap, is to factor an expression, to find the common denominator, or to rationalize either a numerator or a denominator. Okay, so I hope that you have found this video to be helpful. If you did, please like and subscribe and turn on notifications so that you don't miss any future videos. And if you have any questions, then please leave them in the comments. Thank you, and I'll see you in the next one. Bye.